All right, so where did we end off last time? We talked about what the population was, how we could calculate the fitness, and I was very impressed with myself. That explains that. How we calculate the population fitness, just literally a loop for each candidate solution, calculates its fitness. Selection, I'm doing tournament selection because I think it's easy. And it's nice, it works really well. What does it look like? Well, here we go. It's the same that we saw before. This shouldn't startle us. The one thing to note though, like I mentioned last time, is mind the direction here, right? The directionality is going to be important because like for the maximizing a bit string, we want the biggest number. So when it comes to selection and you want to like do tournament selection, let's say you pick 2 candidate solutions, which one do you take? Well, you want to make sure you're taking the right one. So here we want to minimize, smaller numbers are better. So direction is what I want. Did you end up fixing what was your problem with your GA?
Yeah.
What was it?
So I implemented the HRM I sent to you from the book.
Okay.
And then now I realize it's compiling too quickly.
Okay. And then okay, gotcha.
It's like bang.
Okay, gotcha. I was curious if people were getting problems from this, having like the direction set wrong. Variation operators, right. This is right where we left off, okay? Now, this is not there's a crossover topic that we'll have later, where we talk about a bunch of different crossovers. None of them are overly complex, but the point of that topic is to talk about pros and cons and give you ideas, right? But here I'm showing you one particular crossover that works pretty well for permutation representations. Now, one of the things you need to be aware of is, okay, obviously we need to be aware of the issue of, oh, let's get rid of that. Let's close teams. So random, there. Obviously we need to be aware of the whole permutation thing, right? We need to be careful. We want to make sure our chromosomes are still permutations they're still permutations. But other things we want to be aware of is like, and I kind of talked about this before, this idea of like how destructive something is and that exploration and exploitation thing, right? And there's no, like I think we should be really careful about talking about those things as like an all or nothing idea. It's more, everything kind of like exists on a spectrum. So if you think about TSP, one of the things, like, what about a chromosome for TSP is like important, right? Is it that it's a 3 here and an 8 there? It's more like these contiguous chunks that are important, okay? It's not all that's important, but it's these contiguous chunks that are important. So this crossover is going to take contiguous chunks. It's going to attempt to preserve contiguous chunks, but then after the contiguous chunk, it's going to be rather destructive. Like things like the order of the things are going to get moved around a bit. There are other crossovers that are really good for permutations that might really destroy like this contiguousness that we liked. That might work well, and maybe they'll work really well for other types of problems, but it's always, feel around, use your intuition. So, pardon me. Order crossover, commonly used for permutation representations. You will take your 2 chromosomes, keep all the elements between 2 randomly selected points. All right? So, copy the elements from chromosome A in order if they do not appear in chromosome B. It's not too bad, right? So let's say this is A, this is B, okay? So let's say we need to make 2 children. I'm showing you how we make one of the 2 children. So I'm taking this chunk, okay? Then I'm going to start here and be like, 1, does it exist there yet? No, add it. 4. Does it exist there yet? It does. Skip it. 9, add it. 3, add it. 7, don't add it. 8, add it. 2, add it. And then 6, 5 are already there. We're done. That's the idea. Okay? We preserve a chunk, and there is some like orderedness, and I mean order of like the elements, not the ordering of like the data, if that makes sense. The fact like 8, 9, right? Like, okay, 1 and 4, for example. Like, okay, 1, but we didn't keep 4, but we added the 9, you know, like they were still considered in order. Okay, so 1, 9, yeah, yada, yada, yada. And we would do the same thing for the other one, right? So let's say we had 8, 2, 6, 5. Wouldn't copy the 8, copy the 9, copy the 1, not the 2, copy the 3, copy the 4, not the 5, not the 6. Copy the 7, I guess. Yeah. So that's how it would work for the other one. So how would you implement this? And then, okay, here I got really excited because it was my one and only use of an internal function. So order crossover, what are the parameters here? Parent 1, parent 2, start index, end index, okay? Cool. And I've got this thing here. This is the internal function. Let's just make sense of this so we can think about it abstractly in the context of this particular function here. So copy missing elements. Parent, child, start index, end index. Okay, so source index is going to be end index mod the length of parent 1. So what am I doing here? Let's try to re-remember what's going. Let's help me re-remember what on earth I was doing. So end index, okay, is the end index mod parent 1. Okay, interesting. Oh man, I just looked at the projector and I can't see anything. Target index, end index, parent 1. Okay, source. So the end index, okay, let's read this. Copy the missing elements from the other parent into the child. Elements are copied in order that they appear in the parent, starting at the end index and looping to index 0 where necessary. Oh, like looping back to index 0 where necessary and carrying on. Okay. Chromosome 1, chromosome to copy missing elements from, chromosome to have missing elements copied to. Starting index of copied elements, where to stop copying missing elements to. Where to stop copying, starting index, I think it's from the relative to the crossover. So the starting index would be the last, no, let's see, okay. Starting index of copied segment, so starting, that would be like this part, right? Sorry, like this part, okay? And this would be like the ending index. But I'm actually starting at the end. Do you see what I mean? So that's what's going on, okay. Okay, okay, let's keep going. Okay, ending index of the copied segment, where to start copying missing elements from. And then child chromosome with the missing elements copied. Okay. So, well, the target index is not equal to the start index, okay? If the parent at source index, if parent source index is not in the child in that range, so basically if that element's not in there, copy it over. Increment the target index, looping back to 0 where necessary. Otherwise, source index increments. Yeah, so, well, and it can be like, well, which one do I want to move? Let me show you why it's done this way. So if we do copy something over, we have to move the target index and the source index. If we don't copy anything over because the thing at the source index is there, we just move the source index. Let me show you, right? So We're at the 7. Okay, so we go here. 1. Okay, I copy it over. Both move. See? 4. Don't copy it. Only move this one. You see what I mean? So this one's always going to move. This one only moves if we actually move something into it. That's the logic. Oops. Nope. And then when you're done, return the child. Child. This does have a side effect, but it's an internal function, so I'm okay with that. Yeah, okay. And then what are we doing here? If the length of the 2 chromosomes aren't the same, we can't apply it. It's just some error checking. If the start index is less than whatever, just bounds checking, whatever. Otherwise, copy the parents. If start index is greater than end index, I guess we don't do anything. Parent. Where am I? Oh yeah, okay, I see. It just basically makes the copy and then overwrites everything. Oh, that's neat. Okay, I'm impressing myself again. So, all I'm doing, you'll be like, well, hey, you never copied this into a new chromosome. Well, I did by copying the whole chromosome and then overwrote everything with these copy missing elements. That's what I did. So parent 2 to child 1. Do you see what I mean? We copied all of parent 2 and then overwrote the other things from parent 2 with the stuff from parent 1. Or vice versa. From parent 2, you know what I mean. You know what I mean? You know what I mean? There you go. It works, trust me. Great. We will have a full topic on crossover, all right? Where we sink our teeth a little bit more, not only into like how some of these algorithms are going to work, but where we're going to think a little bit more on like, okay, what makes this one good in what contexts, and what other ones might be better in other contexts, and so on. Like we will kind of flesh that out a little bit more. Cool? Before I carry on, was this part clear where I effectively copy the full parent? Okay? I'm not just copying a segment like this one says. I copy it all, but then when I do the copy missing elements, I overwrite what would have been in here. Yeah? Awesome. Okay, mutation. Yes?
Is there a reason that you start at the end index for that copying instead of starting at index 0?
Oh, you mean why start like here and not here? At the end of the day, it's arbitrary. You could do really whatever you want, but I believe the idea is like, well, maybe if these things were at the end of this other parent, and maybe there was a reason they were at the end, right? So maybe we could start copying these things over in order that they appear after. I suppose you could still make the argument like, well, you could still start like here and here, but then things might get a little mixed mash. At the end of the day, you could implement it that way, and I'm curious what kind of effect it would have. But I suspect there may be some intentionality behind like the spirit of like why it was done that way. But I don't really know. I haven't read the paper. But that's an interesting question. Yeah.
It's also just easier to go there because once you get to the end, you just mod the length and you're back to the beginning. So it's only just one. You don't have to check.
Yeah, like what's the difference? Yeah. Yeah, I guess so. And if you do it this way, I guess you'd have to like, if you started here, you'd have to be like, oh, but I'm at that range, so skip, 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 skip. I don't know. Implementation details. It's all about like the idea anyways. This is the idea. This is an implementation of that idea. Just remember that. Okay, mutation. This one, fortunately, is pretty straightforward. You can't just pick an index and change it because you'll destroy the permutation. So an easy way to preserve the permutation is just pick 2 indices and swap them. You could do something fun and crazy like, oh, pick 3 and shuffle where they are. Whatever you want. It doesn't matter. But this would be a nice mutation. What's nice about this one is it's minimally destructive, okay? Meaning a lot will still be there, but it really does, like think of that search space, right? We want our mutation to have an ability to kind of like knock it out of like a local minimum or maximum, for example. So we want it to still have an ability to like, well, yeah, that's a very different location than this one. You know, a lot of it's similar, but like, hey, what if going to 1 to 2 is way better, right? Like we don't know. So it's minimally destructive, but we had an interesting conversation yesterday. It was 2 days ago, whatever day. Was it you and I? About cranking up mutation? Yeah. They had a very interesting idea where, well, this is on topic, off topic, okay? On their implementation, I hope you don't mind me sharing, but this is just a fun idea. Why not try this? Is they checked if there was some level of like convergence that took place. Like if it was some number of generations that went by with minimal to no fitness improvement, okay? Meaning we're probably converged. And when saying that, like think about what that would mean in the simplest like view. Right? Maybe our population's kind of stuck around here. Right? They're all very similar and they're all around here. It's converged. How are we going to get way somewhere else? Now, fortunately, this crossover is reasonably destructive, so it could have a chance to throw something way out, right? But you know, making small changes, that's great and all, but if we've like really converged, maybe we really want to like turn the heat up to like really give it a chance to like knock those points somewhere else in the search space. So if you've started to stagnate, maybe you could switch to like more of a destructive, exploratory fitness in some way. Maybe that just means cranking up the value to make the mutation more likely. Maybe it means change the mutation to an entirely different one that's really destructive. Maybe it means modify. Whatever that means doesn't really matter, but do you see the intuition? How, that's not a bad idea. Change the variation operators in such a way that you hope to get it way the hell out of here in hopes that like, okay, that's good, we found this, that's awesome, elitism, we'll keep track of it, it's there. But wouldn't it be great if we could end up here somewhere? This is a simple one-dimensional search space. I know it's 2 dimensions, but the second dimension is its fitness, right? It's like f of x. You see what I mean, right? I know it's 2D, but really it's only 1D is the one thing I can change, and fitness is what I want to maximize. When we're doing something like TSP, it's way more complicated than that, right? But hopefully this still gives you the idea. Terminate, how do you terminate? I just say run for some number of generations. Did anyone do it differently? All right.
Variation of that cranking of the variation I did was just if we stagnate for long enough, just stop.
Just stop, yeah, okay, end early, great. Yeah, makes sense, yeah. Sometimes you're better off just starting out differently because maybe you'll end up with a population that starts like over here, right? You don't know. Not a bad idea. I've seen some evolutionary algorithms where it is designed to repeatedly, it will run 10 really short GAs, like this was actually in genetic programming, I believe. It ran like some number, let's say 10 GAs or GP runs, algorithm runs, and it would remember where everyone was, and stop everyone and then go back to this one and like carry on. Whatever one looked the most promising. It's almost like it was doing like a starting like breadth first search where it was like, okay, try that path, that path, that path, that, which one looked the most promising and carry on, right? And yeah, it had interesting results, okay? Yeah. And you know, like we would talk about this way later. Let's say, I'm just going to give you an idea, okay? And let's think TSP, not n queens. Let's think TSP, okay? And like we're getting paths that are pretty good, but then we get something like this, right? Right? So like, not too bad, looks reasonable, and then, kind of not so great, but over here. Now, there's no way of knowing, right, unless you like visualize what you're getting, which you should do. But imagine, like, this is a bigger thing. What if there was a way where I could say, like the fitness evaluation is the slowest, most difficult part of the algorithm. What if there's a way for my fitness evaluation to focus on problem areas? Right? It's not to say that these parts aren't important, but what if we kind of like only focus on a subset and maximize that, and maybe that subset can change throughout evolution. The idea is focus the search on the areas that it seems to have the most difficult time with, if that makes sense. Now this isn't a novel idea. People do stuff like this, right? How you go about finding where those difficult areas are and how you focus it is a whole big question. But do you see what I mean? If there was a way where you could actually, like, look, let's not actually evaluate the whole thing. Let's focus on a subset to reduce computation time, but that subset is always focusing on areas that it sucks at. And then maybe it gets better, and then it starts to suck at other areas. And you could think, like, at any generation, if we're only evaluating the candidate solutions on a subset of the data points, it's not going to be very good. But if you think of the fact that, like, well, over the course of evolution, it will see all the data points just as like a moving window or something, right? So it will bake in that information. Do you see what I'm saying? That's a pretty big idea, actually. All right. Okay, variation, mutation, termination. When do I end? Just put it in a loop. And like we said last time, like here, let's go to the actual algorithm, right? I've got some hyperparameters I set, great. I've defined my fitness, and then what do I have? Start with a population, create the population. For each generation, calculate the fitness, select, crossover, mutation, update what the population is, and then once you're done, do one last thing of fitness evaluation. And remember that's necessary because this would make changes, and if we stop the loop, after the last set of changes, we don't know what the fitness is, so we have to run it one more time. You see what I'm, yeah? And if you think back to the maximize, it's the same. We've got our fitnesses, initialization, 4 generations, calculate the fitness. This was bookkeeping stuff. Selection, crossover, mutation, update that. It's the same thing. That's it. It's phenomenal. It's so simple. And this is one of the beauties of evolutionary algorithms is if you know how to do one, you can like apply it to like any friggin' problem you want, which is really cool. And that's like, it feels like cheating, but it works. Right? Like, so raise your hand if you've run the TSP assignment at all yet. Yeah, how many of you are experts in TSP? No. How many of you have spent years studying TSP? Yeah, but you're getting good results already, I bet. It took how long? Not very long. Pretty interesting, right? It's good stuff. All right, yeah, cool. Yeah, so evaluation, selection, crossover, mutation, and then once we're done, do one more. Okay, cool. Any questions about that topic? So like I said last time, one, because we kind of missed the opportunity for that, like, let's play around with the code. from from that other class a couple weeks ago near the beginning of the semester. Let's play around with the code this time. But this time, we're going to apply it to the n queens problem. You have, if you've like forked the repo, you have this on your computer already. You already have n queens. Run. Hopefully it works. Yep, looked like it did. Cool. And look, I found a bunch with like 0 conflicts. Awesome. So you already have a working one, so you should be able to do that. If you don't have the repo forked, you can still go to the GitHub page and like download the scripts and just run them yourself. But that's what I want to do for the rest of this lecture. And now I give you like instructions, okay, on things I want you to play around with, okay? Let's pretend the rest of today's lecture is a lab. I want you to work together, talk to each other, share ideas, and just follow along these steps, and you'll like kind of like learn some things along the way. Cool? Cool. What else do I want to say? Yeah, there we go. And let's draw this board for fun. So 0, 0, 1, 5. There, cool. All right, I guess I will pause this recording for now, and then if we start talking as a group together, I'll just resume it. By all means, I would encourage you to carry on, have fun, but of course, if you're working on the assignment, you're going to get the same thing out of it, okay? But here's what I kind of want to like hit, right? So like this is a nice learning curve, all right? And so we could see at the end of this, it's like, oh, we got to 0, okay? Now, the problem is when you're comparing results, now some of you may know this already, but when you're comparing results, the trouble is like you can't setting, like this is a very like stochastic process. Every time you hit run, you're going to get a different result. So if I hit run once and I get like a 0 is the best I get, then maybe I get like a 2, a 1, a 0, a 2, a 3, a 5, a 0, and so on. I'm going to hit run some number of times, and every time I'm going to get different results. Different results in terms of fitness, but also probably the board configurations will be different as well. Same thing with TSP, right? Every time you hit run, you're going to get slightly different results. And you're going to want to like know, like, well, how good was it doing? So how can I compare, and when I say hit run, I mean hit run with the same settings. If I change the settings and I get results that look like this, and so on, the question is, which one's better? Is there a difference? Maybe there is, maybe there isn't. If there is a difference, is it really better? These are the questions that we want to answer. And the simplest way to go about answering these questions is with histograms. Raise your hand if you don't know what a histogram is. Here's a histogram. It's a nice way to plot a distribution. It's effectively a bar chart, but what you have here is like value, frequency. Okay? So here, I mean, maybe these should be over, but whatever. I hit run, and it looks like I hit run 100 times with some settings, and I got about 15, I'm guessing it looks like. 15 that had a fitness value of 0. I got about 50 with a fitness value of 1, 30-ish with a fitness value. And so you see what I mean? This is plotting how many of those 100 runs that I did, imagine this was 100 lines long, I took each value and plotted their distribution. Do you see? That's the histogram. Now, I would do it such that I would plot one histogram alongside another histogram. Okay? These are now two different distributions. Here's one, here's another one. Okay? I'm guessing this is the, no, I'm guessing the one I showed before isn't one of these two. But do you see, I have two different histograms. One's orange, one's blue. Don't think this weird color, that's just the blue one behind the orange one. Okay, yeah, that's not some third one. It's just like opaque, or ish, somewhat transparent. So here's what I'm doing. I'm like, well, the result of a crossover of 70 and a result of a crossover of 20. And you look at this, and what do you, like, do an eyeball test. What do your eyeballs tell you? What gave you better results? A lower crossover, which is interesting, right? Now, without visualizing the results, it would be hard to make that conclusion, because if you just saw, you kept hitting run, you're like, no, I'm getting a bunch of zeros. Change the settings, I'm getting a bunch of zeros. You might conclude there's really no difference. But when you kind of like think of when you compare distributions, you don't want to compare individual runs, you want to compare the runs in aggregate together, these distributions. And luckily, a lot of times we could do an eyeball test. If the question is, well, what's the statistic? I don't care, it's obvious. You can look at this, I don't need fancy statistics to tell me that I think the orange one's better. Now, sometimes it's not so simple. And the question is, well, and we're going to talk more about probability values a little later. Raise your hand if you've taken your first year statistics. Great. The question is, the question that I want to answer is, are these distributions actually different? Or could they have come from the exact same random variable? Where a random variable is a funny word that the statisticians use to mean, like, imagine there's some box that you're observing and it's spitting out numbers, right? Is it possible that I've got these two distributions that look different, but actually could very well have come from the same random variable? And that's what p-values try to tell you. A p-value tells you what is the probability that these two things are from the same distribution, from the same random variable, really is what I mean. So you can calculate a p-value. For that, you can use, like, without, like, look, I'm no statistician. You might want to do something like a t-test, right? I would recommend doing like a Mann-Whitney U-test. It's kind of like a t-test. It still gives you a p-value. And the p-value gives you a probability, a p-value, p for probability, and the probability will be like 0.13. And that would mean like there's a 13% chance they are from a different distribution. Or they are from the same distribution, pardon me, right? The smaller the p-value, the more convinced you are that they're from different distributions. Because it's how likely is it that they are, I want to make sure I get my blah, 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 blah. A high p-value, if I had a p-value of 1.00, that would say this data definitely came from the same random variable, okay? The smaller the p-value gets, the more we're like, well, I don't know. Now, if you remember statistics, you're like, well, what's the alpha value? And it's 0.05. If it's less than 0.05, it means it's significantly different. Now, that's an arbitrary value. That means 1 in 20 chance you're wrong, actually. That like, oh, like if I get a p-value of 0.04, I go like, wow, okay, they're different. Well, there's a 4% chance, like, right, that I'm wrong. So just be aware of what p-values really mean. But all it does is it tells you if the distributions are different. But just because they're different, like you might have a histogram that looks like this, and your distributions are like this. And maybe a p-value, like, I know it's hard to see, but bear with me. The point is that they're like on top of each other. And a p-value might come back saying like, no, they definitely came from different distributions. But then the question is like, do I care though? Yes, they're different. Yes, the results are significantly different. That setting gave me significantly different results. But does it matter? So then you would want to measure something called like the effect size. And the effect size is a way to measure like, okay, how different are they though? It's a measure of like, okay, they're different, but like, did it matter? That's kind of what you want to get there. And like the reason this is important is like if I spend $1 billion more, I could get a better distribution that is different. But is it worth it? That's kind of like what you want to like check there, right? So like, although it's different, does it matter? And so that's how you're going to want to like compare results. Comparing just like mean values is not sufficient. You want to compare distributions of results to get insight into what you're doing. A lot of times, eyeball tests can tell you a lot, right? I would look at this, like not just a learning curve from one run to help me make conclusions about what hyperparameters to set. I can look at this and be like, I should maybe be trying lower crossovers. This can also help you guide you. Any questions before we wrap up today? Cool. Obviously, we blitzed through this. If you read through this, you're going to get a much better description of this. That might help you for the assignment. Otherwise, I'll see you Monday, because we have lecture Monday, right? Yeah. You seem, do we? All right, yeah. I know, right? I feel the same way. Okie dokie.